All right, this is long, so we're going to split it into three parts. So we're talking about the Earth, Moon, Sun system. So this is us. This is astronomy dealing with our immediate area. So Earth, ancient observers used to think the Earth was flat. It is. There are still people who do. If you would like to watch this video, go ahead. I'll leave it up long enough to where you can go watch flat earthers. You can get stuck in flat Earth theory for a very long time. There is simple ways of figuring out how the Earth is not flat. For one thing, everything else in the universe is spherical because sphericals objects are more likely to survive in a space-like setting. Another thing is gravity. Gravity, as something falls towards the Earth, you see that it doesn't just fall flat; it falls at an arc if it is thrown. So no matter where you are on Earth, they will fall towards your center of the sphere if you drop it. So that means that it is the core. Because we know we have a core, that means we have a center of gravity. That means it will fall towards the center of gravity. The Earth's shadow on the moon in a lunar eclipse is always curved. So we know it is a curved surface. It can't be that. It's very simple to see that. And of course, they go with, you don't even have to have pictures of the Earth. You can just see based on these facts. People in different parts of the world see different stars on their horizons. If it were flat, we would all see the same stars. Uh, you have to see that this makes sense. So as you're turning, you see different stars. Not everybody on different sides of the, or not everybody in China can see the same stars we do, and not everybody in Australia sees the same stars as China. So gravity is the attractive force between two objects depending on their masses. So if we look at the Earth has a higher center of gravity than we do, but we have a higher center of gravity than the atoms that flow around us. Same thing goes with the moon. So the moon is a poles between the Earth and the moon, creating this constant tug of war. We see this based on our tides in the ocean, but we'll get to that in a future one. So Earth's magnetic field, different portion, we're not talking about gravity anymore, deals with the poles between our north and south pole. This is because of the convection or the movement in the Earth's core. It creates a magnetic field around the Earth. Uh, the axis is tilted 11.7 degrees from the geographic axis of rotation, meaning that we are at an angle. This is what gives us different seasons. So the Earth's magnetic field protects us from harmful radiation. You can see that there are this radiation based on the aurora borealis or the northern lights. So the field resembles that of surrounding bar magnets. So like if we have a magnet that you see on my wall, if you have any class, you can see that there is some sort of field, or feel that there is a field that protects it or pushes away other magnets of the same type. This is what happens with our solar wind being pushed around the magnetosphere. So you can see this is the sphere that is created around a bar magnet. The location of the Earth's changed slowly over time. So about every 200,000 years, they switch. So the North Pole becomes the South, and the South Pole becomes the North. This doesn't mean we change directions based on what we see, but it does mean that the magnetic pole changes. So North South, the South Pole will become the North, and the North Pole will become the South based on magnetic pole. So, like I said, the aurora borealis, is the northern lights. So the electronically charged particles colliding with the magnetic sphere or the atmosphere, creating this light. So we have our magnetic field. It protects us from that harmful radiation, but you can see the radiation when it's closer to the poles. So as they get closer to the poles, these charged particles will start to go towards these poles, creating these lights. And I highly suggest looking at this because they are very cool to look at. I think in the 90s, the particles were lit up enough to where you could see it close to here, like in northern Missouri. But you have to live closer to the poles in order to be able to see these aurora borealis and aurora australis, which is the southern hemisphere. Sorry for the yawn. So when we talk about the orbit of the Earth around the sun, so we are on a heliocentric model. We are not on an Terra-centric or an Earth-centric model. Heliocentric is only like we know the sun is the center of the Earth, or the center of the Earth, center of the solar system. So everything goes around it. So planet Earth has an orbit around it in the shape of an ellipse. An ellipse is kind of like an elongated circle. So this means that you'll have 2 points, and it will follow that elongated circle or elongated curve and come across those points. So we have several points that we call it, but we'll get into that to our next one. So the closest the Earth is to the sun is in early January, and the furthest away is in July. So Earth is in what we like to call the Goldilocks zone. We talked about this in our last lecture. So Earth is in the Goldilocks zone that creates this perfect area known for solid, liquid, and gas water, which makes it possible for life. We have an oxygen rich, which supports our life. The atmosphere, even without plant photosynthesis, has enough oxygen in it for us to survive. Sorry. So based on orbits, we have created a method of timekeeping. So the Babylonians started 3,000 years ago. And because it is based on 60, they divided a circle into 360 parts called degrees. So now they basically created the spherical idea, or how a circle is put into degrees. So degree, of course, is that symbol. So we have our method of timekeeping. So we have 60 seconds, 60 minutes, but it takes 24 hours for the Earth to revolve on its axis. So the spinning causes the sun to appear to move across from east to west, but we know it's just because the Earth is spinning. The Earth spins 360 degrees in about 24 hours and then spins through 15 degrees in 1 hour, meaning that a time zone is 15 degrees wide. So, and for convenience, we put it around city and state borders so that way there isn't a confusion into where you're in two different time zones in Atlanta, Georgia, or something. You want to make sure that you're in the same time zone if you're in the same city. So the international dateline is the only way to time travel. So as you move across the international dateline, you can either move into the future or move into the past. So when you move from Los Angeles to Tokyo, you are actually going forward in time. But when you go from Tokyo to Los Angeles, you're going backward in time. Meaning that this is where time changes based on the day. So this is based on the coordinated universal time. And that's how we all work on schedules, especially in a world like today, which is so worldwide economy driven. Remember, rotation is going to be measured in days, and revolution, which is a full orbit around the sun, is measured in years. So rotation is on its axis, and this is showing the sun to night, so day to night, and revolution is the motion around the orbit. So that is measured in years. So as it moves across the sky, it seems the sun and stars are in fixed positions, but they will seem to move. So if you go out and look for Orion's belt tonight, you'll see it is or the Big Dipper. They are going to be in different spots right now than they are in January or in July even. So it's pretty interesting to see how the stars move across the world. So revolution is measured in years. It is an elliptic. We call one revolution or one orbit an elliptic because of the path it takes. And that is all for today. So watch this. You'll be done. Good luck. Talk to you later.